Okay, so I'd like to talk today about another distribution. We've been talking about the binomial distribution. I want to talk about another one today. This is in section 4.7. It's called the Poisson distribution, and it is quite important in applications. So let me pull up a whiteboard. Okay, so 4.7, the Poisson distribution. Okay, so remember that the binomial distribution involves repeated Bernoulli trials. By Bernoulli trial, I mean we perform an experiment and the outcome is either success or failure, and success occurs with probability p. In the Poisson situation, you're also interested in measuring successes. You have a random variable x, and you're measuring the number of successes, maybe in some unit time, and the PMF has inputs 0, 1, 2, etc. So all natural numbers, not 0 through n. We're performing the experiment over and over and over again. And so there's a parameter that's used in this, and I will motivate this below. Lambda, it's a real number, and it's the average number of successes that occur. For example, suppose you're at a warehouse and you're waiting for orders to come into the warehouse. Say you work in Amazon. A certain number of orders come into the warehouse per minute, and we can take the average number of successes per minute, and that will be lambda. Okay, and then the PMF for the Poisson model is P of K is given by, and this is going to look weird initially, but I'll explain where it comes from, e to the minus lambda, lambda to the K over K factorial, where e is 2.71828182818354535, etc. Okay. So that is the definition, and it really is a PMF. Okay, so this is really a PMF because the sum, as k goes from 0 to infinity, of P of k is given by the sum, by the definition of what we gave it, e to the minus lambda, lambda to the k, over k factorial, k going from 0 to infinity. And we can factor out e to the minus lambda, and then what's left over is the sum of of the sum of what? Lambda to the k over k factorial. And this sum is the series, the Maclaurin series for e to the lambda. So this is going to be e to the minus lambda times e to the lambda, and that gives me 1, which is what I needed to get to have a PMF. So this really does work, this as a PMF. Okay, so what's the motivation behind all of this? The motivation is actually the binomial distribution. We're going to take n to infinity in the binomial distribution BNP. Okay, so in order to make sense of this, suppose we do n experiments and n gets very large, and p is the probability of success. So how many successes do we expect in the n experiments? Well, you would expect on average p times n successes. Average p sub n, p times n successes occur in n trials. So let's set lambda equal to p times n in the binomial distribution. Okay, so then what's the probability of x equals k? That's p of k in the binomial random variable, and that's going to be n choose k, p to the k, 1 minus p to the n minus k. But remember, we're taking n large, so we're going to take n going to infinity. And let's see what we get. Well, this is the same thing as the limit as n goes to infinity. First of all, what does n choose k? That's n factorial over n minus k factorial times k factorial. And what is p? Well, p is lambda over n, so we're going to get lambda over n to the k. And then you get 1 minus lambda over n to the n minus k. Okay, now I want to rewrite this in the following way. I want to, first of all, let's put the limit back in. Okay, so what I'd like to do is rewrite this as n factorial times n minus k factorial times 1 over n to the k times lambda to the k. I'm just breaking up pieces of this product times 1 minus lambda over n to the n times 1 minus lambda over n to the minus k. Okay, so now what the heck do I get here, right? So I get, first of all, I get that what happens as n goes to infinity? Well, this lambda over n is going to 0, and we're going to get 1 to the minus k. So this term goes to 1. Oops. Tends to 1. What happens to 1 minus lambda n over to the power of n? This is one of the definitions of e to the minus lambda. That's how you define e to the x, okay? If you go back in your Calc 2. All right, so then what do we have here? Oh yeah, so I forgot the k factorial. I'm going to put the k factorial that appears on the previous line over here. And so we're going to get a lambda to the k over k factorial. Oops. And notice that this expression here is my Poisson distribution. So what's left over that we have to consider is this term here. So what is this term over here? I'm going to do this calculation over here. So let me make some room. Okay, so what is n factorial over n minus k factorial? Well, that's n times n minus 1 times n minus 2. And everything cancels after n minus k plus 1 from the quotient. So what this left-hand factor that I have of this product is just a product of n all the way down to n minus k plus 1. And now, what is 1 over n to the k? Well, that's in the fraction. It's going to give me an n times an n times an n. And how many factors are there? There are k factors, and the numerator has k factors. And this should be viewed as a polynomial. The top is a polynomial in n of degree k, and the bottom is a polynomial in n of degree k. And you learned from Calculus 1 that this limit will tend to 1. It's the coefficient in front of n to the k in numerator and denominator, which you're going to take the quotient of, and that's going to be, in this case, 1. So this is going to tend to 1. So this expression tends to 1. So in other words, at the end of the day, this expression is going to be equal to, in the end of the day, it's going to be equal to e to the minus lambda to the k over k factorial, which shows you that the binomial distribution, when n goes to infinity, tends to the Poisson distribution. And so that's the idea behind it. Okay. So before I move on to calculating its expectation and variance, with every random variable, we want to calculate the expectation and variance. I want to sort of indicate what kinds of applications there are of this stuff to the real world. And I'm not going to do any applications today, but my next lecture, I'll do some applications. Okay, so let me erase the screen. Okay, so applications. So I'm just going to mention three. The book mentions more. In printing, we could look at the average number of errors per page in a printing process. That would be we would expect that to follow a Poisson model. Orders coming into a warehouse, you would expect to be Poisson, assuming the average number of orders per minute is constant. Okay, three, the number of particles omitted, I should say, emitted, I should say, by a radioactive substance per some unit time. Okay, so these are three possible applications of the Poisson distribution. Okay, so let me talk about the expectation then. The expectation of the Poisson random variable goes like this. What is E of x? By definition, E of x is the sum. Well, you have to take the values of x. X is going to be going from 0 to infinity. And you're going to take k times the probability mass function, which is e to the minus lambda, lambda to the k over k factorial. Now notice when k equals 0, the first term you're summing in the summation vanishes because k will be 0. So this is the same thing as the sum k equals 1 to infinity of k over k factorial, but k over k factorial is k minus 1 factorial, and then we get e to the minus lambda, lambda to the k. Now what I'm going to do is I'm going to take out a lambda and make a lambda to the k minus 1. Okay, now what I'm going to do is I'm going to set j equal to k minus 1, and let's see what we get. So if we set j equal to k minus 1, I get lambda sum. So k starts at 1, so j starts at 0 to infinity, e to the minus lambda, lambda to the j over j factorial. But wait, we saw this is the PMS, this is the sum of all the values of the probability mass function. This is 1, this sum. We saw that this sum was 1 on a previous slide, so we get lambda as the answer. So what do we conclude? We conclude that the expected value of the Poisson random variable is lambda. Beautiful. Okay, so let's save that. And let's clear the screen because I'm actually going to now I'm going to work towards the variance. So in order to compute the variance, I'm going to compute first the expected value of x squared. So that would be the sum as k goes from 0 to infinity of k squared, e to the minus lambda, lambda to the k over k factorial. Now the procedure is more or less the same. It's just a little more elaborate, the same as when we computed the actual expectation. So what I'm going to do is I'm going to factor out a lambda first of all. And notice when k is 0, the first term in the sum vanishes, so we can start off at k equals 1, and it'll give you the same answer. And then we have a k left over, and one of the k's cancels with the k part of the k factorial. So what you get is e to the minus lambda, lambda to the k minus 1 over k minus 1 factorial. And now we're going to set, again, the same trick. We're going to set j equal to k minus 1. And this will be lambda, the sum j equals 0 to infinity, j plus 1, e to the minus lambda, lambda to the j over j factorial. And what does that give us? Well, I'm going to break this up. This is lambda times the sum, j goes from 0 to infinity, j e to the minus lambda, lambda to the j over j factorial, plus 1 times, I'm distributing the j plus 1 times, so it's going to be a sum, j goes from 0 to infinity, of e to the minus lambda, lambda to the j over j factorial. Now we saw what each of these terms is. So each of these terms, let me change the color here. The color yellow doesn't really work out well here. So this sum is equal to lambda. Now the first term we computed previously, this was the expectation, and we got lambda. And the second term is the sum of the values of the PMF, so that's 1. So this is going to be lambda times lambda plus 1. Okay, that's great because now we can compute the variance as the difference between the squares. So let's clear the screen. So the variance of the Poisson random variable is given by the expected value of x squared minus the expected value of x quantity squared, which is, we saw lambda times lambda plus 1 minus lambda squared. And if you do the algebra, you get lambda squared plus lambda minus lambda squared, you get lambda. So here's our summary so far. The expected value of x is lambda, and the expected value of x squared, the variance of x is also lambda, and this is only true for a Poisson random variable. By the way, what do I mean by a Poisson random variable? I mean any random variable with PMF given by P of k equals e to the minus lambda, lambda to the k over k factorial. Okay, so that is that. I just want to basically reiterate what the assumptions should be in a Poisson random variable. So let me, the Poisson model, if we apply this to the real world, we should make some assumptions. So one, the average number, so if we're thinking of like the warehouse case, the average number of events or successes, if you like, so that could be an order into the factory per unit time should be constant. Now this in the real world is typically not true. It's approximately true at certain times of the day. You might expect that orders coming into a warehouse, an Amazon warehouse, between maybe 3 and 4 in the afternoon should be roughly the same as between 4 and 5 in the afternoon. That's an assumption. Okay, and the second case, and by the way, lambda is the average number of orders, the average number of successes. Okay, and then the events of success should be like in a Bernoulli trial. The events, the successes, or the events that occur every time we are independent, as in a Bernoulli repeated Bernoulli trials, as in the binomial distribution. Okay, so that covers what I wanted to say today. We will do some applications next time. So have a good one.